Ever wonder how companies predict their sales for the next quarter? Or how Zillow gives you an instant estimate of your home's value? Well, a lot of the time, the secret sauce is a tool that's surprisingly straightforward but incredibly powerful: linear regression. So today, let's pull back the curtain and really demystify how this thing works.
Our story starts, weirdly enough, with this guy, Sir Francis Galton, and a really odd question. What on earth does the height of a father and son have to do with predicting your salary? It sounds completely unrelated, right? But believe it or not, his work back in the 19th century laid the groundwork for the exact models we use today. It's a wild connection, so let's unpack it.
You'd think one of the most fundamental tools in data science would come from, computer science or math, but nope. It was actually born out of biology, from a study on how traits are passed down through generations.
So Galton was painstakingly plotting out the heights of fathers and their adult sons, and he noticed something fascinating. Sure, tall fathers usually had tall sons, but on average, those sons were just a little bit shorter than their dads. They were drifting back, or regressing, toward the average height of everyone. He literally coined the term regression toward the mean to describe this.
And that was a huge light bulb moment. If you can spot and model this tendency for height, what else could you model? What other relationships are hiding in the data? This core concept, that we can describe these tendencies to predict an outcome, is the absolute heart of what linear regression is all about.
Okay, so how do we get from that biological observation to modern machine learning? Well, it's all about one simple goal: finding a single straight line that best cuts through all our data. The famous best fit line.
First things first, we need two kinds of variables. Over on the left, you've got your independent variable, which we'll just call x. This is the input, the thing we think is causing a change. A classic example is years of experience. Then on the right, you have the dependent variable, or y. That's the output, the thing we're trying to predict, like salary. The whole game is to figure out exactly how x affects y.
And how do we do that? Well, as Analytics Vidya puts it so simply, the goal is to draw a line through our data points that gets as close as possible to all of them at once. In other words, we want the line with the absolute minimum amount of error. But how does a computer even measure error?
It does that using something called residuals. Okay, so imagine each data point is a person's actual salary. The residual is just the vertical distance between that actual point and the point where our line predicted their salary would be. Every single data point has one. These are all the tiny individual mistakes our model is making.
Now, to get a single grade for the entire line, we use what's called a cost function. The most common one is mean squared error. The machine basically takes every single one of those residuals, squares them, which just makes them all positive and punishes bigger errors more, and then finds the average. That gives us one number, one final score. The lower that score, the better our line is.
So the big question is, how does the algorithm find the one line with the absolute rock-bottom lowest score? It uses this brilliant process called gradient descent. The analogy from Analytics Vidya is perfect here. Imagine you're standing on the edge of a giant, U-shaped valley, and your goal is to get to the very bottom. You take a step in the steepest downward direction, feel the slope, and then take another step in the new steepest direction, and you keep doing that until you can't go any lower. That lowest point, that's our best fit line.
All right, that's enough theory for now. Let's make this real. We're going to walk through how you'd actually build a model to predict someone's salary based on their professional background.
The process pretty much always follows these 4 steps. First, you load your data, all that good stuff like age, experience, job title. Then, and this is super important, you split it. You take a big chunk of the data, the training set, to teach the model. The rest of it, the testing set, you hide away. It's like saving the last chapter of a textbook for a pop quiz to see if you actually learned the material. Finally, you take your trained model and see how it does on that data it's never seen before.
So during that training step, the model is churning away, doing that whole gradient descent process we just talked about. It's looking at all the patterns and relationships in the data, and what it spits out at the end is a mathematical equation. It's our very own salary prediction formula. And with that formula, you can make actual predictions. For instance, using the model from our source material, if you plug in a 30-year-old male data scientist with a bachelor's degree and 5 years of experience, the model predicts a salary of $74,470. It's not just a guess, it's a specific, data-driven number.
But, getting a prediction is easy. The hard part is knowing if that prediction is any good. How do we actually evaluate our model and figure out if we should trust it? One of the best things about linear regression is that it's not a black box. You can look right inside its equation. See these numbers called coefficients? They tell you exactly how the model is thinking. For example,
If the coefficient for years of experience is a positive 5,795, that means for every single extra year of experience you get, the model predicts your salary will go up by about $5,800, all other things being equal. It's super clear and easy to understand.
Another really common way to grade your model is a metric called R². Just think of it as a score from 0 to 100%. It tells you how much of the difference in people's salaries can actually be explained by the factors in your model, like experience and education. So an R² of, say, 80% means your model explains 80% of the salary variation. A higher score seems better, right?
But here's where we get into some really interesting territory. Can we just chase that high R² number and call it a day? Is that one number really the whole story?
Let's look at a fascinating case study from the blog Statistics by Jim. Some researchers built a linear model to analyze something called electron mobility. And the result? They got an incredible R² of 98.5%. I mean, come on, that's practically a perfect score. You'd think they could just publish and be done with it. But then they looked closer. Despite that amazing R², the straight line was just wrong. It was systematically over-predicting in some spots and under-predicting in others. There was a clear curve in the data that the line was totally missing. A more complex, non-linear model, however, hugged that curve perfectly. And just look at the standard error, a measure of the average mistake. It was a massive 72.5 for the good linear model, but only 13.7 for the non-linear one. That R² score was totally hiding the truth.
And this brings us to the most crucial takeaway of this whole thing. You cannot just rely on a single score like R². You absolutely must check your residuals. When you plot out your model's errors, they should look totally random, like you just threw a handful of confetti at the chart. The second you see a pattern, a curve, a cone shape, anything, you know your model is biased, no matter how great its R² is.
So this all brings us to the final and honestly the most important part of the entire process. Not just building a model, but choosing the right tool for the job and really understanding its limits.
So let's just quickly recap the big ideas. Linear regression, it's a fantastic, powerful, and easy to understand tool. It should almost always be your starting point. Keep it simple. But remember, a high R² score isn't the finish line. It can fool you. The real goal is to build an unbiased model, and the best way to check for that hidden bias is to get your hands dirty and actually look at the residual plots.
And that leaves us with a final question to think about. Remember that electron model? It had a 98.5% R². It was simple, it was interpretable, but it was fundamentally, systematically wrong. So that begs the question, if a model is simple but wrong, is it actually useful at all? It's a question that really gets to the core of what it means to build a truly good model.